In this video, we'll take a look at a commonly used statistic for assessing how well a linear model fits some data. We'll illustrate that statistic in the context of an example. And the particular example we'll look at now is a model for predicting the average crawling age of babies from the average temperature when the babies were 6 months old. There are 12 data points, one for each month of the year. And we can see that the average crawling age in these data range from 28.6 weeks in one of the months to 33.8 weeks in another month. We could summarize the variability that we see in the crawling age by its standard deviation. Here's the formula for standard deviation. In this video, we're going to focus just on the part of the formula that includes the data values. That is, the sum of the squares of the differences between each value of y and the mean of all the y's. Sums of squares, like this value, play an important role in statistics. In regression, this sum of squares, that is, again, the sum of the squared differences between the values of y, which in regression is our response variable, and their mean, is called the total sum of squares. We can visualize the deviations that make up the total sum of squares in this plot. We'll draw a horizontal line at the mean crawling age, the mean of y. And we'll add some purple vertical lines which show the distance from each y sub I, that is, each value of the crawling age, to its mean. To find the total sum of squares, we'd square the length of each of these purple lines and add them up. The resulting sum is called the total sum of squares again. It's a total because it can be broken down into two components: the part of the variation in the y's that can be explained by the regression line, and the leftover part, the variation in the y's that is not explained by the line. Let's talk about the first of these two components, the variation in the y's that is explained by the regression line. This is called the regression sum of squares. It is the sum of the squares of the distance from each of the values of y predicted by the line to its mean. To illustrate the sum of squares, let's look at the values that the line predicts. They fit exactly along the regression line. We'll add a horizontal line at the mean of y to the plot, and we'll add these red vertical lines. The distances that contribute to the regression sum of squares are the red vertical lines. These are the distances from the predicted values to the mean of y. The sum of the squared distances that are illustrated by these red lines is the regression sum of squares. And again, it is the variation in the y's that is accounted for by the relationship between y and x. The final component of variation is the error, or residual sum of squares. It is the variation in the y's that the regression line does not explain. Its formula is the sum of the squares of the vertical distances from the data values to the line, which are illustrated by the blue lines in this plot. We've seen this sum of squares before. In order to find our regression line, we found the slope and the intercept that gave us a line that minimized this sum of squares. Summarizing all these sums of squares and how they're related, we have the total variation in the y's, the total sum of squares, is equal to the variation explained by the regression line, the regression sum of squares, plus the variation that hasn't been explained, the residual sum of squares. This decomposition of the variation in the y's leads to a statistic that can be used to assess how well the line fits the data. The statistic is called the coefficient of determination, but is more commonly referred to by its symbol, which is r squared. R squared is the proportion of the variation in the response variable that is explained by the regression line. That is, it's the proportion of variation in the y's that is explained by the linear relationship with x. We can calculate r squared as the regression sum of squares divided by the total sum of squares. We can also think of it as 1 minus the proportion of variation in the y's that is not explained by the regression line, which gives this alternative formula for r squared. R squared is a proportion, so it's always a number between 0 and 1. A small value of r squared, near 0, means the line is not explaining much of the variation in the response variable. And a large value of r squared, close to 1, means the line is explaining much of the variation in the response. So why is the coefficient of determination given the symbol r squared? Well, r is the symbol commonly used for the correlation between two quantitative variables. And mathematically, it can be shown that r squared is the square of the correlation between the response and predictor variables. For our example, the relationship between age when babies can crawl and temperature, r squared is 0.49. So that means that 49% of the variation in the crawling age is explained by its linear relationship with temperature, and then 51% is unexplained. The correlation between average crawling age and temperature is the square root of r squared and is negative 0.70. Note that the correlation is negative because the relationship between crawling age and temperature is negative. R squared, on the other hand, is always positive, so r squared never indicates whether our relationship is positive or negative. Now let's look at another example. This example shows how atmospheric concentration of CFCs was growing over time from 1977 to 1990. The points are very tightly scattered about the line, so we expect a very high value of r squared. And indeed, for this example, r squared is 0.996. So for these data, 99.6% of the variation in CFCs is explained by its linear relationship with time. So the line is explaining almost all of the variation in the response. But that doesn't mean that there isn't a better model for these data. For these data, we have a systematic pattern of points above, then below, then above the line. So a model that captures that pattern would be preferred. R squared is a useful statistic, and it's often quoted, but it doesn't tell the whole story. A large value of r squared is desired, but there are no general rules for how large is large. In some contexts, there is lots of natural variability, and then r squared tends to be smaller. While in other contexts, there is naturally less variability, so then we would expect higher values of r squared. Moreover, a high value of r squared does not mean that a linear model is best. As we saw with the CFC example, we can get a very high value of r squared, even though there are other systematic patterns in the data other than the straight line. It's even possible to get a very high value of r squared in situations where the linear model is definitely not appropriate. In this illustration, we have no relationship between y and x. But if we add one more point that is high leverage and influential, we'd get a linear relationship with a high r squared. However, this linear relationship and the resulting r squared are meaningless since they depend on just one point. We've been looking at regression models which just have one predictor variable. These are called simple linear regression models. Multiple linear regression models have more than one predictor variable. With them, it is possible to make r squared very large by fitting more and more complicated models. But overfitting the data with complicated models typically results in a model that does a bad job at fitting new data points. So, especially when using multiple regression, relying on r squared as a measure of the fit of the model can be deceptive. R squared gives us one indication of how well our linear model describes our data, but it should never be relied on for the whole story. It's essential to use other tools, such as scatter plots, in order to fully understand the nature of the relationship between any two variables.